Here's the final application that I want to get to. Okay, and this is related to the Google PageRank example from earlier, but I'm going to make up a totally unrelated setting. Here's what I thought of. Pretend every time Michigan and Ohio State play their annual football game, if Michigan wins this year, there's an 80% chance they win again next year. I'm going to try and represent this graphically, using this sort of graph with directed edges. Okay? If there's an 80% chance of Michigan winning next year, given that they won this year, one way I could represent this is with a self loop with the weight 0.8. So this is representing, if right now Michigan won, 80% chance of winning next year. Okay. So if there's a 0.8 there, that also tells me something else about another edge that needs to be in this graph. What else has to be in this graph? Yeah.
1, 2, find out OSU.
Yeah, what this is saying is, well, if Michigan wins 80% of the time in back-to-back years, well, then 20% of the time, if they've won, Ohio State's going to win the next year. Okay? And let's suppose Ohio State, not as good, but still okay, 70% of the time will win next year if they won this year. So that gives me a 0.7 here, which means a 0.3 here. Okay? And so you can think of this graph being just defined in terms of conditional probabilities of next year given this year. Okay? And this type of system is one in which eigenvalues and eigenvectors are often applied to. That is, systems that evolve over time. So if this were like a differential equations class, or like a physics or electrical engineering class, you'd study eigenvalues and eigenvectors a lot for that purpose. Okay? And we'll look at some of, not the electrical engineering examples or the physics examples, but examples like this, which the Google PageRank example essentially is for our purposes. Okay, what am I going to do with this? Well, my question is, in the long run, what percentage of games does Michigan win? That is, okay, I know if they win this year, I know the probability of winning next year. And if they lose this year, that is, if we start here, I know the probability of winning next year. But what about just in general? What is the probability of them winning? That is not directly answered from this graph. Okay? And here the numbers are relatively small, so you could do some conditional probability, arithmetic to figure this out. But in general, you have to imagine we have many more states than just Michigan and Ohio State, right? Like, if you're thinking about the internet, well, the internet has trillions of nodes in such a hypothetical graph. Okay, what I'm going to do is take this graph and turn it into what I'll call an adjacency matrix, A. I don't know why that was so triggering. Right, I figured that's what it would be. And in an adjacency matrix, each column, at least for our adjacency matrices, each column is going to describe the movement out of a node. That is, the first column will be Michigan to what? And the second column will be Ohio State to what? And the rows will represent the inputs to a node. So this first row will be into Michigan, and the second row will be into Ohio State. So there are 4 numbers here, so presumably this is going to go in a 2 by 2 matrix. What's the top left number? 0.8. And what's the, well, let me not use colors here. 0.8. And what's going to be beneath that? 0.2, good. So the columns in my adjacency matrix are going to sum to 1. Now this depends on what class you're in. Like if you, I don't know, are taking stat 425 or something, maybe they'll define it in the transpose. But for our purposes, we're going to look at it this way. What's going to go in the top right? That is the chances of moving from Ohio State to Michigan? What's that going to be? 0.3, which means here we have 0.7. Okay. So, first, before we move forward, are we comfortable with how we went from this graph with edges to this adjacency matrix? We see how these four numbers came from these four numbers, generally? Okay, good. And again, you're going to practice this in homework time. Let me rewrite this adjacency matrix. 0.8, 0.2, 0.3, 0.7. Remember, what does this have to do with my question of, in the long run, what percentage of the time does Michigan win? Well, what I can use this adjacency matrix to do is like simulate the universe, where I can say, okay, let's pretend we're going back to prehistoric times. In year t equals 0, or k, we'll use k. In year k equals 0, let's just pretend Michigan wins. We start with 1, 0, okay? We'll simulate. So in year 0, we'll say, let's pretend just we know for sure Michigan wins. And let's pretend x sub k represents the probability of Michigan winning and the probability of Ohio State winning in year k. We okay with that? So that is xk equals p Michigan and p Ohio State in year k. Okay. What does the universe look like in year k equals 1? And how do we get there? That is, if we go back to this graph, like let's see whatever we're about to come up with should tell us the intuitive answer, which is, if Michigan's winning this year, for sure, what are the chances they win next year? 80%, and the chances they don't is 20%. So whatever calculation we do should give us a vector with 0.8 and 0.2. And what do you think that calculation is? Yeah.
A times xt.
Yeah, you just multiply by x0. Right? And here that'll give us 0.8, 0.3, 0.2, 0.7 times 1, 0, which gives us that 0.8, 0.2, which means if we start in a year that for sure Michigan won, then next year there's an 80% chance that they'll have won that year. Okay? Then what about the year after that? Yeah.
Should say x1.
Yeah, you just multiply by x1. And I have the numbers pulled up here. It ends up being 0.7, 0.3. Things looking less good, but still pretty good. And if you unwrap this, all we did is we took a squared, and that's where these matrix powers come from, as I mentioned earlier, multiplied by your initial condition. So in general, the universe at time step k looks like a to the power of k multiplied by your initial condition. Because to advance this simulation one time step forward, all we do is multiply by a. So multiplying by a steps one iteration into the future. So how could we use this principle to answer our original question? In the long run, what percentage of time does Michigan win? I have this way of simulating the universe. I ran it a few times, right? I said, okay, let's pretend Michigan wins our first year. And then the second year, there's an 80% chance they win. Third year, there's a 70% chance they win. You might notice that these numbers, like even though we're repeatedly multiplying by a matrix, they're not massive. They still, for some reason, still add up to 1. So what do you think I could do to answer my original question, which is in year 1,000,000, what's the chance that Michigan wins? What could I do? Yeah.
Maybe take the limit as k approaches infinity?
Yeah, why don't we just pick a really big k and see what the output vector is? Okay? Now, so far, this has nothing to do with eigenvalues and eigenvectors. It's just a fun problem. And this is exactly what I did in the notes. I said, for k in range 1 to 15, compute a to the power of k times x. First, I'll note that a star star k, while it may look like a to the power of k, it's not that. What this will do is raise each element individually to the power of k, which is, that's only a to the power of k if a is a diagonal matrix, which in general it's not. Okay? So in general, to raise a matrix to a power, you use np.linealogy.matrix power. Okay? And so I said, okay, let's try x1, x2, x3, all the way through x15. And let's see, do these values converge to something? It seems like they're converging somewhere. Where are they converging to? Yeah.
0.6 and 0.4.
0.6, 0.4. What do you think this example has anything to do with eigenvalues and eigenvectors? Yeah.
Eigenvalues for A.
Close. This is an eigenvector of A, corresponding to a very specific eigenvalue. Okay? And let me quickly show you which eigenvalue that is. So here's the big idea. And so I'll say C notes for code. Actually, no, in case someone doesn't look at the notes for this, this is too important to not see. Copy this. Here's the big idea. xk approaches an eigenvector of A. It should not be obvious why this happens. Like, just looking at this, it just seems like a coincidence. But the sort of thing we're going to study in homework 10 and the next few lectures is why this happens. But really quickly, let me just give you a sketch of how you would show this to yourself that that's true. And I'll add, in addition, corresponding to lambda equals 1. In other words, this x you end up finding corresponds to ax equals x. And intuitively, this may make sense, right? We're looking for the state vector where if you advance one step in time, it doesn't change anything. You've already converged. Do we agree with that? Right? Like, the states we were looking for are the ones that don't change. And if they don't change, well, that corresponds to an eigenvector with an eigenvalue of 1. And then if you go here and just take 0.8, 0.2, 0.3, 0.7, multiply it by x1, x2, and solve for x1, x2, well, then you get 0.8 x1 plus 0.3 x2 equals x1, 0.2 x1 plus 0.7 x2 equals x2, and you solve, and like before, you're going to get infinitely many solutions. Right? This is a matrix, and if there's an eigenvalue for that matrix, well, then any scalar multiple of that eigenvector, if there's an eigenvector for that matrix, anything on that line is also an eigenvector. But what's the added condition we introduce to make x1 and x2 a valid state distribution? Yeah.
Is it the iteration of a to the k times the original one? And because we said that approach is.
That's how we got here. My point is, if you solve this, you could find like x1 equals 3, x2 equals 2. Like, this solves it. What additional criteria do I add on so that the vector x I find actually has something to do with our scenario?
Yeah. Add this sum to 1.
Yeah, that they add up to 1, so they're valid probabilities. Yeah. So what I end up finding is that x is some, well, I'm not going to use k here. I don't know. Let's use c times 3, 2, add condition that x1 plus x2 equals 1. Why can I just add that condition? Well, I can add any condition I want, because any of those things on that line are an eigenvector. We saw NumPy already added its own condition, which is it'll give us the unit vector. But being a unit vector is not the same as adding up to 1. I just add the additional add up to 1 condition because I want to interpret the numbers as probabilities. And when I do that, I end up getting that C should be a fifth. And so the eigenvector that adds up to 1 and also has an eigenvalue of 1. The 1 is appearing in two different places, right? It's here and it's the sum of the things in here. It's this one. Okay? Now your question is, why is this what it converges to? I mean, there's the loose explanation of, well, intuitively, if there's a solution to the system, it would be the one with an eigenvalue of 1. But why is there an eigenvalue of 1 in the first place? Like, why did this have a solution? And why did it converge to this eigenvector? Like this matrix, it has another eigenvalue. Its other eigenvalue, can you tell just by looking at this?
Like 5.
Yeah, it's going to be a half, right? Because we know that the two eigenvalues are going to add up to this plus this, which is 1.5. So the other one has to be 0.5. Like, why did it converge to the eigenvector with an eigenvalue of 1? That's a good question. The short answer is that these dynamical systems always converge to the eigenvector with the biggest eigenvalue. So the biggest eigenvalue of a matrix tells you a lot about its system. Okay, but more on all of that when we come back next time.